Welcome to Brain Vision.
In this question, we're looking at hydrogen atoms being irradiated with photon of wavelength 85.5 nanometers and having their electrons ionized from the atom. So basically the electrons become free. Now we want to find what is the maximum kinetic energy, assuming that the hydrogen atoms are at the ground state. So at the ground state, the amount of energy required to ionize the hydrogen atoms would be 13.6 eV. And given the energy of the photon, if we subtract away 13.6 eV, the remaining amount of energy would be the kinetic energy of the ejected electrons. Right, and so what we need is the energy of the photon, which in this case is taking hc over lambda, which is just 1240 eV dot nanometers divided by the wavelength in nanometers. This will get us the energy in terms of electron volts, which is about 14.5. And therefore the kinetic energy, or the maximum kinetic energy of these electrons would be 14.5 minus 13.6, which is about 0.9 eV. Now, however, we are actually told that some of the electrons actually show kinetic energy of 10.2 eV, and we are asked how is it possible, right? 10.2 greater than the current kinetic energy. So the kinetic energy observed is actually 0.9 plus 10.2, which is like 11.1 eV. Now, I hope you find this 10.2 a bit familiar, right? Because this is actually the energy difference between the n equals to 2 and n equals to 1 states between the hydrogen atom, right? As you remember, energy for the hydrogen atom is given as negative 13.6 eV divided by n squared. So for the first level, this is negative 13.6 eV, but for the second level, it's 13.6 divided by 4. This is 3.4 eV, right? Minus 3.4. And we see that the energy difference is 10.2. Right? So what this tells us is that some of the electrons or some of the hydrogen atoms could have been on the n equals to 2 state rather than the ground state. And this is actually by Boltzmann distribution, right? At temperature at some equilibrium, thermal equilibrium, there can never be a perfect scenario where all the hydrogen atoms is in the ground state except at 0 kelvins, right? So if you have some temperature, there will definitely be some distribution between 1 and 2, although it is definitely more biased towards the n equals to 1 state, right? Only a few of the hydrogen atoms would be in the n equals to 2 state, but that is enough for these electrons to actually exhibit much more kinetic energy, right? Because it will only take 10.2 eV. Sorry, it will only take 3.4 eV to ionize the atom if it were in the n equals to 2 state. and therefore the remaining amount of energy that will be imparted as kinetic energy for the electron will be just 14.5 minus 3.4, which is 11.1 eV, which actually explains the discrepancy between what was calculated prior using the ground state hydrogen atoms.